Hello, my name is Paul Ebreo, and this is my presentation for the December 2021 Chicago Python Group main meeting. I've been a ChiPy member since the mid-2000s. My day job is in C#, but my personal projects are in Python. I'm by no means an AI expert, but I know enough to spot limitations in the current approach. About a month ago, I was hospitalized for brain surgery. I saw limitations firsthand from speech recognition to how the old brain impacts everyday life and how the new brain, if still functioning, can still create this presentation. For months now, I've been ruminating on machine learning, but being in the hospital crystallized all these issues, and it it's formed the answers of what was nagging me. The agenda for this talk will be the following: the upcoming AI winter, the old brain versus the new brain, a brief tutorial of how current machine learning works, the limitations and my proposed solutions for machine learning, and finally, resources you might be interested in if you're interested in this topic. My talk will give plenty of examples and is organized into least speculative to most speculative. That is, least uncontroversial to most controversial. AI winter. We first start off with an AI winter. An AI winter is when there is a stagnation or a lull in funding and increased pessimism of the field in general. The first winter was in the 70s. The second winter was in the 90s. Then Deep Blue came in 97. Deep Blue beat the chess grandmaster Garry Kasparov in 97. Then there was IBM Watson in 2011, which won Jeopardy! Then the biggest boon for AI was DeepMind's Go in 2016, which really propelled AI. However, the dirty secret of current AI is that it suits these large companies' business models. Large amounts of photos, video, text, voice, etc. Data are funneled into these companies, which they use to train their machines. The status quo works for them, and it's advantageous to them. However, I predict that their approach will hit a wall. Maybe not this decade, but it will hit a wall, and a new method must be adopted, or else we'll never reach artificial general intelligence. Old brain versus new brain. We start with this video of a frog that uses the old brain. Notice it does not know or care that its food is real or not. It just sees it and reacts to it. This is similar to my surgery. Why did I suffer speech impairment, walking impairment, etc.? Yet I can still be aware enough to make this presentation. It's because the old brain and the new brain are distinct. The old brain, or lizard brain, just acts on stimulus response, just like this frog. Whereas the new brain memorizes and imagines. More details on that later. We'll start off with the training data first. To start, the old brain requires more training data because it has no model of the real world. It is just, as I mentioned earlier, working on a stimulus response mechanism. It just reacts when it encounters some stimulus. Now, generalization. What does generalization mean? It means being able to deliver pizza, operate a nuclear reactor, cook a meal, ride a bicycle, etc. It means being able to pick up skills once, then apply those skills to other endeavors, and not having to relearn a new set of skills. An example would be learning how to tell stories and being able to speak or write them with just a couple of times practice, not hundreds of thousands of examples. This picture captures what I mean. On the very left is an illustration of the old brain, or lizard brain. Current deep learning uses the old brain approach. On the very right, we have the new brain, which I'll make proposals for so that we can achieve this style of learning. Right now, current AI systems are just stimulus response. They're operating like the old brain. We need to upgrade to a new brain approach if we're to achieve artificial and general intelligence. Machine learning, an intro, or the current way of doing things. At the heart of machine learning is training and recognition. We start with a set of training data that we feed to the machine to tell it what it should recognize. It learns what to categorize or not to categorize with a cost function. That cost function depends on a bunch of numbers called weights and biases. For illustrative purposes, those weights and biases are just knobs that set the result of our cost function's output. When the output of the cost function spits out the right value, we say we've tuned the knobs just right. We can save the state of our knobs or numbers, and we'd save this model. A model is just a file with a given set of numbers in order so that our cost functions has the lowest result possible. In Python, here's what a cost function could look like. Just outside that is the input and output neurons. A neuron is just a thing that holds a number. That neuron/number holds the grayscale values of a pixel or the volume of a sound. One layer of neurons is connected to another layer of neurons and can be represented as a matrix of numbers. See three blue, one brown's videos for an excellent explanation. More modern machine learning systems employ this technique plus a bunch of others. We mix and match those techniques to achieve our machine learning goals. But at the heart of it, we're just trying to reach some optimal maximum or minimum by setting the knobs. The hidden layers workings are hidden to us, but at the end all we can control are the input and output layers. Limitation 1. The need for massive amounts of data. The first limitation is that current ML requires a lot of data. We see this by the techniques used by GPT-3 OpenAI, whose model takes about 175 billion parameters, or a multiple of 175 billion knobs. The problem with GPT-3 is that it uses a massive amount of text data, but humans still have to pick the ones that make sense. This video illustrates this. In this video, a guy has a conversation with a human embodiment of GPT-3 and it spits out evil nonsense. Evil that it condones murder, and nonsense that its answers are not consistent. Here is a snippet of the interaction. Human. What is accomplished by killing people? GPT-3. Nothing. Human. So rockets and EVs are useless, but accomplishing nothing by murder is useful? Explain that one. GPT-3. It is fun. Later in interaction. Human. So if I find rockets and EVs fun, according to your logic, doesn't that make them useful? GPT-3. No. Another example is a parking simulation where it takes the car about 300,000 tries to park correctly. It wouldn't take a human this many times to get decent at parking. In a way, we are brute forcing the computer to learn. Technically, we're not, but it feels that way. More recently, in September 2021, during Tesla AI Day, the head of AI, Andrej Karpathy, says he wants an LCD dataset. In other words, a large, clean, and diverse dataset. When he says large, he means that there should be plenty of examples of a stop sign, for example. When he says clean, there should be stop signs should be labeled as stop signs, not pedestrian crossing. And diverse in that there should be stop signs in spring, summer, winter, fall, day or night, whatever condition. To feed its AI that LCD training set, they used simulations at Tesla because they couldn't get LCD otherwise. I'm going to propose that this is a dead end if they want to realize their goal of Tesla Bot, a humanoid robot that can navigate the world like a human. The reason I believe this is because there was news the other month that OpenAI is bending the robotics initiative. This is a sign, I believe, that they recognize this approach won't work. To overcome this limitation, Tesla employs simulation plus a fast chip to retrain their AI. Because Tesla sees new things every day because of its massive fleet, it has to recompile its ML model almost every day. It takes about 72 hours and about millions of dollars a day to maintain the server farm that they use to create their model. They had to redesign a new chip to be faster and cheaper per unit of compute because current machine learning is so expensive, it has to be done this way. This sounds like I'm a negative towards Tesla. I am not. For the given limitations, they're solving these problems with hardware and software. A faster new chip, with simulations to create examples, so as to create LCD data. I'm just pointing these limitations out and proposing a new way forward. Solution 1. Assumptions. The way we train for data is by dialing in the right knobs using a cost function. This is way better than brute force permutation, but there's an even better way, by baking in assumptions. An assumption is just an expectation. These two pictures look the same, but when we present them right side up, we see they are different. We see that our brains think they are the same, but our brains are making the assumptions that lips and eyes should face a certain way. Illusions are just images that manipulate the pictures so that our expectations are taken advantage of. In this case, the assumption this illusion takes advantage of is the fact that lips and eyes should be in a certain direction given the face. We know in programming that we can vastly speed up an algorithm when we add in assumptions. This is also true for ML. Assumptions are what makes processing real-world data faster. The problem with current machine learning and AI is it makes no assumptions about the data coming in from the real world. That causes you to need a lot more data. Limitation 2. The causal model of the real world. As I said, current machine learning is just a stimulus response process. If we look at this example of a dog being followed by two chicks, we see another example of the old brain working. The first animal you will probably see is your mother. So 99.999% of the time, it's fine to treat it as your mother. The solution to this problem is to add the ability to model the real world. I'll propose you'll need at least three things to solve this. You'll need memory, senses, and imagination. With memory, you'd be able to recall things, like what happened in the past, what worked, what didn't. With senses, you'll be able to see, touch, and hear those things. And with imagination, you'll be able to picture the future that you want to happen and to do the things that need to happen to make that happen. You'll need all those things to be able to reach our causal model of the world. Only then will you have enough to make an artificial general intelligence machine. A couple of examples of imagination and causal relationship of the world at work. Here's an example of an imagination in a game Breakout. Notice that the machine sees what could happen given a certain move. We do this in everyday life. Here's another example. Here we have an example of a whale understanding that it gets two fish, a big than usual reward, for catching a single bird. Review. To recap, we can break down the talk into two limitations and the proposed solutions for those limitations. First, the current way of doing things requires too much data. We can solve that by baking in more assumptions into our algorithms. Second, we have no causal model of the real world. To solve this, we have to add memory, senses, and imagination to our machine learning algorithms. Here are some resources you might be interested in.